Welcome to the Muxall Open IoT channel. I am your host, Michael Crane. Okay, sorry, you have to bear with me here. I'm dealing with a little bit of a cold. But in today's video, we're going to, I don't even know where to start with this video. So we're going to look at the the LCD corruption issue that I posted about on our Facebook group. And I'll put a picture of what it looks like when I'm editing the video. As you'll see, the LCD screen was having a bunch of after images, if you will, and just basically a bunch of garbage. And this was on the V5, the new version 5 main PCB. And so, why is there a version 5 main PCB, you might ask? Well, that's a good question. So we have to go back to what prompted all this. And this is the ESP32 made by Expressive Systems, I think. But this is the ESP32 Pico. And they must have made millions of these boards back in 2018 and 2019. And probably 2019. I think the date code on this chip is 2019 on this one. But as you can see, it's not much to it. But it was kind of goofy. This was if you notice, all the electronics and buttons are on the wrong side. So they put female headers on it and expected people, I guess what they were thinking, they used to have pads on the bottom, rubber pads on the bottom. They expect you to set this on your table and then plug wires in the top of this, to do testing. And that's fine and dandy for testing, but if you need to connect it to a board or want to stick it on a breadboard, you had to use some male headers and plug it in your breadboard. Then you couldn't access anything under here, so it was a bit backwards. So they realized this probably after many people fussed about it, and so they developed a new one in 2021, I believe. And this time they put male headers on the back side of the board, all electronics is on the top, and you can just plug this right into a breadboard to do testing or whatever you need to, and life was good. But I had designed, this is what the version 3 and version 4 look like. They have male headers coming up out of the main PCB, right? And this thing right here, this ESP32, just kind of plugs into it like that, right? And if you own one of these Muxalls, you've likely seen this. This has the Wi-Fi antenna. This is the internal antenna. This is the board I mod for the external, so on and so forth. So I kept buying these, even though in 2021, or it might have even been in 2020, they started making these. Because I had, maybe a couple hundred of these boards, and everyone had these the ones with the female headers in stock. So it wasn't that big of a deal, right? And in 2022, I went to order more of these guys, and lo and behold, there wasn't a person on the planet that had any more of these ESP32s with the female headers. And you might be saying, well, wouldn't it be easy just to unsolder these guys and and change the header out? And the answer is no. It is a mess, and it'd take an hour, and it would just be a mess. So thus, I had to design the version 5. This is actually version 5.3. I don't know if you guys can read that or not. But I designed the version 5.0 or 5.1. I don't have one around here right now. And this board right here is designed to be able to take the new model So what I had to do is, remember, it was originally like this on the old one. I had to basically flip this guy around like that, right? Hopefully you guys can see that. Sorry, my focus seems to be messing up. Sorry about that. So anyway, I had to flip it around like this. And of course that involves moving all the traces around, and basically everything on this side got moved over to this side and flipped over and moved around and so on and so forth to accommodate this male header. Now this is actually much better for my application because this thing just plugs right in like that, and I can, nice and I can just solder that baby right in. You know, sweet, right? And so I flipped everything around, had, I don't know, 10 boards made, shipped over here, soldered this guy on here. Actually, this is it right here. This is the controller. Got everything soldered on there, and plugged that baby in, and and the LCD was corrupt. That started this whole investigation and the whole reason for this video. So, you know, the first knee-jerk remote, thought that I had is, oh, I screwed up the design of the PCB. So I started looking at the design of my PCB, and I'd show you a picture of it, but I accidentally overwrote it when I was making changes, so I don't have the original design to show you. But it's not important, because that's not actually the problem. But we'll get to that in a minute. And then the other thing I did is I soldered some of these wires on here, on the SCL and SDA lines, and on the ground, and put it on the scope. And we'll step over to the computer here real quick, and I'll show you what I saw. Okay, so I put this on the scope, and oh, okay, yeah, there you go. This is much better. So this is actually a picture that I posted on the Facebook group, and you can see. So here's a start condition right here, and then you count 1, 2, 3, 4, 5, 6, 7, 8, and then the 9th. So you got eight bits for the byte, if you will. And then this is the ACK, and this is the ACK coming from the LCD. And as you can see, it's not quite ACKing completely. This should be getting pulled all the way down to ground, or pretty close to ground. And so the spec says that it needs to be at least 30%, needs to be lower than 30% of VCC, which is about 1 volt. So it needs to be about right there somewhere before I2C protocol recognizes this as a valid ACK. So without having a valid ACK, the master controller, or the controller, the ESP32 chip, assumes it's a NAC, and NACs can be held, they can either retransmit or stop, or there's a couple other conditions that I don't really remember off the top of my head. But anyway, all of them aren't good. So anyway, we were getting this, and I was like, okay, well, what's happening is it was corrupting it. So I guess it was trying to retransmit or something. I didn't really chase it down too much of what it was corrupting. I just knew this was bad, was probably causing all the problems. So then I went on the hunt to figure out what this was. And of course, like I mentioned earlier, my first knee-jerk reaction was, oh, I messed up something on the PCB, and let me go, redesign the traces. Okay, so this is version 5.3/5.4, and here's the LCD connector right here. I know it's very busy. It's kind of hard to look at. Anyway, this is the LCD connector, and these two lines right here, which are very hard to see, this line and this, oh, here you go. Yeah, see, this is the SCL line, Here's the SDA line. And what I originally had done is I had ran the lines this way and up. And these are the two pull, R14 and R15 over here. These guys right here are the pull-up resistors, right? And here's the pins going into the ESP32. And so I'd originally ran these the SDL and SDA lines this way and right up here. And you can tell it's very tight right in here, right? And I had to move these grounds around and I had to, actually I think I deleted that ground. I just moved this one out of the way. And so when there was a couple things that made me think, okay, well, maybe it's picking up a bunch of noise because these traces are running along all these pins, are running by all these pins. They're running pretty close together, so there might be some crosstalk. And another thing is I moved this ground way over here somewhere, right? And I said, okay, well, maybe it's not able to, maybe I introduced a bunch of, resistance or something like that. I doubt if it was inductance, but like resistance in the trace that was causing the LCD not to be able to pull down the SDA line, right? So then what I did is I went ahead and I said, okay, well, maybe that's a problem. So I moved everything up around here and I shipped those boards off because I had 3 customers waiting for controllers. I'm like, I could not find those ESP boards anywhere, the older ones. And so I had to hurry and try to get these V5s fixed, right? And so I paid $600 to have some 5. I think it was version 5.3 at this point, boards made. And here are those boards. 16 main PCBs for $600. and so I went ahead and I didn't put the whole thing together. I just kind of put a female header on each one and plugged an LCD in it, button panel, and fired that baby up, and lo and behold, sorry, it was probably out of focus there, and lo and behold, that thing didn't work at all. It didn't fix it one stinking bit. That was lesson number 1. So one of the things I forgot to mention is before I put the button panel on here, I just plugged in one of the newer ESP32s on here and tested it on the scope. The make a good ACK, a relatively good ACK. It worked, and then as soon as I put the button panel on, it stopped working. And I said, "Baha, we've got a capacitance problem on the I2C line, on the SDA line." So I pulled up the Citronics ST7528 control driver data sheet, and I don't know if you call it a 97-page documented data sheet, but it is what it's a spec, I guess. All right, so I start looking through the spec, looking for the the max capacitance. I said max capacitance. Actually, the max rise time and fall time. Fall time's usually never a problem. It's the rise time because of the pull-up resistors, right? And you'll see you can see the curve on the SCL line right there. Let me pull up that other picture. That was a little better. Anyway, you can see the you can kind of see how it's curved and not perfectly square, but you can see right here that this is a nice straight line, right? And these are a little bit curved. That's okay. You get, like I say, you get that from the pull-up resistors because it's got to pull through the 5K resistors, right? That's the whole RC constant business. But this right here, this straight up line right here, this should have been an indication. We'll get to that later. Anyway, so I was looking at this and I said, well, 300 nanosecond, right? Max rise time, yeah, not a problem. It's not a capacitive problem. Yeah, this is a little better picture right here. Yeah, I mean, it's a little rounded on the top, but you know, you go from 30 to 70%. Is it within the 300 nanoseconds? Yeah. I'm not going to measure it. It's just, I knew it was okay. So I was like, okay, you know, the SDA line looks fine. You know, pulling it down, you can see the controller had no problems pulling it down, but the LCD couldn't pull it down, right? You can see a little bit of the curve on top of this pulse right there, but yeah, it just wasn't able to pull it down. And so another thing I did, I forgot to mention, is I slowed it down. I went from 400 kilohertz to 100 kilohertz, and I didn't have any problems, other than it was slower than dirt. At 100 kilohertz, it would pull this down. It wasn't perfect, but it'd pull it down, you know, somewhere around here. So it was able to pull it down. And so I'm like, okay, so usually capacitance and the pull-up resistors are what limits the bus speed, right? Because if you have too much capacitance, you get too big of a RC or too big of a RC time constant, and you can't run as fast on your I2C bus. So I'm going through this data sheet going, oh, okay. And I finally get down to this strange little note down here. By connecting SDA out to SDA in externally, the SDA line becomes fully I2C interface compatible. And that's actually very important. It'll handle up to 400 picofarads of capacitance on the SDA line. All right. But you know, okay, so you keep on reading. Having the acknowledge output separated from the serial data line is advantageous in chip-on-glass applications. And you might say, why is that? And it goes on. It says in COG applications where the track resistance from SDA out pad to the system SDA line can be significant, a potential divider is generated by the bus pull-up resistor and the ITO track resistance. And ITO, I had to search around to find out what that means, and I don't remember off the top of my head, but it's, suffice it to say, it causes a potential voltage divider going from by this ITO track resistance and the chip on glass. It says, it is possible during the acknowledge cycle the ST7528 will not be able to create a valid logic 0 level. Aha! That is interesting information. It says by splitting the SDA in input from the SDA output, the device could be used in that mode. That ignores the ACK bit. Okay. Yeah, that's probably not going to happen. But it is interesting that they're saying, okay, chip-on-glass applications, we have this ITO track resistance problem that creates a potential voltage divider. All right? Is everyone with me so far? Okay, so to help understand a little bit of what I'm talking about, you can see this is the pull-up resistor right here. This is a master slave. It's showing the resistance right here on the master side, but just think of it like it's over here on the controllers. I'm sorry, on the slave side. And what what that note was talking about in that spec sheet is this resistance right here, because of the ITO track issue, can get very large. You can see this is there's two resistors, right? And if this one gets very large, then it's not going to be able to pull the it's a voltage divider, so it's not going to be able to pull down far enough to make a logic 0. I hope that makes sense. And this document, by the way, is very, very good if you ever want to read it. It's when, why, and how to use I2C buffers. Because I was thinking about using a buffer, just saying, well, okay, I don't know why it's not able to pull down, other than, what they said is in here that, there's too much track resistance, or there's too much capacitance on the line. And so I'm scratching my head and kind of going, oh boy, do I really want to, stick another chip on this board without really understanding why it is failing? Okay, so after mulling it over for a bit, I decided, well, it's time to roll up my sleeves and just dive in head first into this circuit and figure out what in the world's wrong with it. So, armed with my Art of the Electronics second edition book in one hand and Google in the other hand, I set out on a mission. And so the first mission was I needed to find out the capacitance on the bus. So we've got tau equals RC. RC is the time constant. And so we want to solve for C. And watching this video here, this is a good little video. It goes pretty fast, but it's kind of nice. It's only 7 minutes long, and it's how to measure the time constant with an oscilloscope. Since I have an oscilloscope, I thought this was very appropriate. So, with the oscilloscope, we can find the time constant, and from the data sheet, we should be able to find the resistance. And let me back up a little bit. I think I got ahead of myself. So we know the resistance of these resistors right here, right? These are like 5K or 5.1K or something like that, pull-up resistors. And there's also a built-in pull-up that's a very weak one on the SP32 that's enabled by the wire library I use for the I2C. And Expressive, who makes the ESP32, said that the internal pull-up's around 50K. So it's very weak, and it's inside the chip. And but I dug through their information and found out it's actually between 10K and 100K. So they use 50K as a rule of thumb. Go figure, right? So we know the resistance, right? And we can measure tau. So now we can solve our equation, right? We've got tau, we know our resistance, we should be able to solve for our capacitance. So, since Expressive gave such a large 10K to 100K range on their internal resistance for the little pull-ups, the internal pull-ups on the chip, I decided, here's a chip by the way, I decided that I would measure it, okay? And so on this board right here, I pulled the chip off very carefully off the SDA line, and this resistor wasn't there, of course, and put my scope back on there, and lo and behold, it didn't make any difference at all. Now that 5K resistor should have been at least twice as strong, strong being providing more current, than even a 10K. Even if the internal pull-up was 10K, the 5K would still allow, twice as much current, right? And of course, if it was 100K, it'd be even more than that. So I was really surprised. I was like, wow, I would have thought the thing would you remember how the SCL line was curved. I expected the SDA line to look pretty curved like that too. So I said, okay. I said, let me measure the current through. This is the new one right here. I said, let me just measure the current through this guy, and so I can calculate the resistance on it, because you can't really measure the resistance through it. But if I put my probes across it from the SDA line to ground, I should be able to measure the current that is going through there and calculate, what the resistance is, right? V equals IR. So, and I'll do this. Let's do this. Okay, so I went ahead and hooked up my flute here and put it on microamps, and because with a 50K or 50K, between 10 and 100K, it's not going to have much current between it. And like I said, Espressive mentioned that they use 50K as a rule of thumb for their pull-up resistors inside the chip. So yeah, it should be pulling microamps. So now to let you know, I did the SDA first. And then I had to do the SCL because I was a little bit surprised with the SDA. But anyway, I don't want to be spoil the fun, so I'm going to go ahead and plug it in. And as you can see, there's about 70 microamps being pulled through the chip there. And so I did. I don't know if you guys can read that. Probably not. So I did the math. And it's this one right here, and that came to about 47K pull-up, which is about what Espressive said. They said it's about a 50K pull-up resistor inside the chip. And that was actually my sanity test, because if I move this guy over here to the SDA line, let me move this up to milliamps, and let's see, DC relative. Okay, let's plug this guy in now. Oops. Look at that. 8.4 milliamps. I mean, and when I first saw this, I was blown out of my chair. I was like, oh my God. And actually, this isn't the board that I tested this on. It was I think this one or something like that, but I'd done some other mods that I'll tell you about here in a minute. But yeah, so I calculated out, okay, well, it should have even at 10K, it should have only 330 microamps. This thing had, the one I measured actually had 10 milliamps. I mean, it was order of magnitude more than what I expected, right? And that came to 330 ohm pull-up resistor. I mean, that's the equivalent, right, of a 330 ohm pull-up resistor. And if you remember back when when we're looking at the edge of the SDA line, and I said, see how straight the SDA line edge is, and I said, keep that in your mind. That right there should have been a sign that there was or something providing a lot more pull-up current than just my little 5K ohm resistor, but I didn't catch that. So then I start going down the rabbit hole. So then I knew something was up, and I knew it wasn't inside this chip right here, because even Espressive says 10K to 100K max. There's no way they're going to put a 330 ohm pull-up resistor inside this little bitty chip. It would drain all the current out of it, right? So I knew it had to be something on this board that was providing the 330 ohm pull-up resistance. And it was just a matter of, okay, let me find this thing. Okay, so I start looking at the boards, and the new one's on the left, the old one's on the right. You can tell with female headers. Sorry, this picture's not very good, and I didn't really want to go take another picture of this board. I've spent enough time on this project. But anyway, I start looking. I'm comparing chips. Okay, what's changed? I don't see anything, and so I pull up the schematic for this, and of course, so here's the ESP32 chip right here. You can see it right here, and I got the power supply, USB, switch buttons, connector. Okay, so our SCL line is on this GPIO 0 right here. The SDA line is on GPIO 4 right here, okay? And GP stands for general purpose, IO is course input output. And that's not very helpful. Anyway, so we need to find, what's connected to this guy, and so I look and I say, okay, well, it's connected to this switch button. Oops, go away. It's connected to this switch button right here. And it's got R6, which says it's a 0 ohm resistor. I guess that's to disconnect it if you don't want to use it. And then it's showing this, little capacitor right here. And I'm looking at this going, oh, okay. Well, this could be a problem, right? And I'm looking at this thing, and so I go back to the picture right here, and you can see here's the little resistor, here's the cap. The cap isn't installed, and I'm kind of curious. I thought it said not installed. I don't know why it doesn't say not connected on this one, but they didn't. One of the other data sheets say something like not connected or something like that. That's another thing about this Espressive stuff. Sometimes the data sheets there's different versions of them. You really have to be careful. I just downloaded this thing. I'm surprised it's got an error like that. But anyway, as you can tell, that it's not connected, right? It's not connected on the old one either. It's got this resistor. They both have the resistors, but there's no pull-up, right? So then I go ahead and say, okay, we might as well go all the way down the rabbit hole. And I got to, looking at where these, I'm like, there's no pull-up resistor. Something's got to be feeding power to it, right? So this is the switch right here, and I know it's kind of hard to see. It takes a while. Let me see. Yeah, okay. So here's the switch. Here's the two pads. This is the cap that's not installed. This is the resistor right here. And this, I believe, is the bottom of the board. It's hard to tell. I don't see any labels, just a dimension. Anyway, you can see right here, here's the resistor, here's the cap. I believe this is going to ground. Anyway, you can see a trace runs up comes up through here, goes underneath this transistor, then runs up here, and then runs into this transistor pad. And then goes up here, goes into a via, and comes over here, all the way over, and then, hold on, all the way down here, sorry, and then boink, right into GPIO 0. All right? And I'm like, oh, okay, so why is it going into this transistor right here? And this is the collector of the transistor. And so I come back over here to this drawing, and I'm like, okay, let me do a search on IO0. And I do a search on IO0, and it brings me down to this right here. IO0 that goes into the, I know this transistor is very confusing. It's flipped over, which this is very confusing. Anyway, this is a collector, it's an emitter, this is the base. Anyway, it's going into the collector right here. And then it, comes, and then it goes off into that via. So, where are we here? So if we follow this via right here, oh, this is the top. Oh, so we were looking at the top earlier. There's a ground layer. This looks like probably power. Here's bottom. Okay, here we go. So you can see it comes, here's the via right here. It comes up and it goes over, then goes over to IO0 right here. And okay, so this is so from here down through the via, and then hold on. Through the via, then up here, then down here. This is all we need. So we don't need any of this. And so what I did on that other board that I said that I had already modified is I took my knife and I basically just cut that trace right there. Because I'm like, well, we don't need any of this crap. The only thing we need is we just need it to go to that pin over there. And lo and behold, after I cut that trace, I fixed the problem. You can see the ACK is still, it's not completely down to 0, but that's okay. The delta Y right here, I have my cursors on it, measuring how high it is, about 200 millivolts, which is a whole lot better than the 2 volts or 1.5 volts or whatever it was earlier. And everything is running hunky-dory now. So here it is comparing them. Sorry, it's not quite the same scale, but you can see here's the ACK. You can kind of barely see it, right? It's just right here. And here's the ACK down here. And you can see it's quite a bit better. I mean, this was a good 1.5 volts or something, and which would never fly, because it's got to be under 30%. So I found the problem, I fixed the problem, I know how to fix it. The V5s will work without any problems now. But I was still left with the nagging question, what in the world was feeding voltage to this thing? I mean, we measure a 333 ohm pull-up resistor around here, and there's not a resistor anywhere in this. And that's when I had to break out the old Art of Electronics book. So I pull out, excuse me, my Art of Electronics book, and chapter 2, I guess I didn't catch the page, it's not really that important. But if you look right here, this shows an ohm meter's view of transistor terminals. And It's an NPN transistor. I looked it up in the spec for this board right here, and you can see that, yeah, current can easily flow from the base to the collector. And so, when we are trying to pull this line low, current was flowing out of the base, from the base of this transistor and up into the collector. As far as I can tell now, right? Another thing too, I guess it could be, and I'm not going to research it anymore. It's got to be coming from this transistor, but I guess it could be coming, you know, reverse bias from the emitter to the collector. Maybe there's some kind of breakdown in the NPN junction there or something. I really don't know, and I'm not going to investigate any further, but I did want to mention that it might not be coming from the base. It could be coming from the emitter side. I'd have to look at the circuit and do some more research on it, and I'm not going to do that. So I stopped debugging at this point. At this point, I was like, okay, I've done my root cause analysis. I've fixed the problem. I know where the problem, at least I have a good idea where the problem came from. I'm happy, right? So I'm very confident, and this transistor is the only place it could be getting power. And by the way, I did verify that once I cut this line, I did another calculation. We could look at it on the bench, but suffice it to say, it looks like the SCL line now. Now there's like 50 k ohm or so resistance on the SDA line, and that, my friends, is that. I probably have maybe 20 or 30 hours in this problem. And by the way, the fix is actually very simple. I just clipped this transistor off, and we're good to go. So there you have it. I hope you liked this video. If you have any questions or comments, leave them in the comments under the video. I'll try to answer them the best I can, and I'll see you guys next time. Don't forget, you can support the Muxall Open IoT channel by donation using a credit card and PayPal, or by purchasing products at the Muxall store. Details and links are in the description under this video. Well, that's it for this video. If you liked the video, give it a big thumbs up, that helps, and hit the subscribe button, that really helps. If you have any questions or comments, post them in the comments under this video. Thanks for watching, and I'll see you next time.